parler depuis mon secondaire. Alors, so now I'm going to switch to English. Hopefully that works for everyone. So, as was explained, this presentation is a synthesis of a number of projects and studies that have looked at different aspects of the carbon and nitrogen cycling, and especially the fluvial exports that we've observed at Cape Bounty over the last 10 years or so. So you'll notice there I have a lot of co-authors acknowledged here. They've all contributed in one way or another to different aspects of this work. So this is a photograph of our camp at Cape Bounty. We now have a lovely lab tent. It's our tent where we eat and cook and confirm our individual sleep tents here in the front. So this is what we've named West Lake. We have such imaginative and creative names here, as you'll see. So Cape Bounty is what we've called the Arctic Watershed Observatory. It consists of an integrated research program that's been running now since 2003. And it's now the longest running observatory of its kind in the Canadian High Arctic. We've looked at basically the overall sort of aims of everybody working there is to really get an integrated understanding of how climate and landscape and permafrost change is influencing the hydrology, the biogeochemical responses, and this includes everything from aquatic systems as well as terrestrial ecosystems and landscape perturbation. So really this is the kind of picture that we're trying to understand. Climate has direct impacts, obviously, on hydrology, how much water flows, where that water comes from, and the disturbance and thawing and depth of the active layer, disturbance of the permafrost, and then that obviously has impacts on both aquatic and terrestrial processes, sediment fluxes, nutrient fluxes, as well as the movement of metals in the environment. So this is more or less where Cape Bounty is on the southern coast of Melville Island. And this is a map of what we've called West Watershed, West Lake, and East Watershed, East Lake. And all these different dots, we have 3 met stations that in the catchment. Main met is the one where we have most of the vast majority of the meteorological measurements. East and west are just rainfall and temperature. And then these other sites are where we have hydrometric stations. We have a number of stations within the lakes where we collect suspended sediment, and we have moorings to monitor various things there. We have a flux tower up here, as well as a ITEX vegetation experiment site. So there's a lot of stuff going on there. My work has been primarily focused at looking at how the hydrology and permafrost disturbances have affected the fluxes in the rivers. So a lot of this work was, initiated after 2007. We had a very extensive series of permafrost disturbances that occurred in the catchment. 2007 still stands as the warmest year on record at Cape Bounty, but also on record in the region. And so following this really warm July weather, which propagated very deep thaw, we also had some pretty significant rainfall events that led to the development of active layer detachments. And this all happened at the very end of July in 2007, just as we had pulled up all of our instruments, we're getting ready to close down camp. So all of the data that I'm going to present from 2007 really is all pre-disturbance data. So I just point that out so you have that for reference. Because everything that happened after the disturbance, we weren't actually there to collect samples and monitor it until 2008. So this is what east and west catchments look like in terms of the extent of disturbance as of 2010. So there were over 100 active layer detachments that formed, and overall the west watershed, so each of these polygons here, the brown polygons are active layer detachments. West watershed had about 2% of the catchment affected, and the east relatively less. And the other thing about the disturbances in the east is that a lot of them were not hydrologically connected, so the flow network wasn't really affected by them. Some photos of what those look like. So they're the scar areas. Basically, all of the soil has been removed and moved down slope, and in most cases, it accumulates. The material accumulates down slope just like a rug if you slid it down the stairs. And it sort of piles up with the vegetation and surface soil, leaving behind mineral material that's sitting over what used to be the frost table. So I'm realizing I'm talking to the geography department. I know from my own home department, a lot of geographers purposely avoid chemistry, so I threw in some basic chemistry here to help make sure that everybody gets to sort of keep up on things. So now I'm going to go in to talk about the impacts of these disturbances on the carbon and nitrogen fluxes. So before I get there, I thought I would just make sure we're all on the same page in terms of what carbon it consists of and where it comes from. So when we look at fluvial carbon and the types of carbon on the landscape and where it comes from, it really breaks down into two things: the organic matter, and that's the stuff that's the broken down bits of terrestrial and aquatic biota. So it comes from the roots, plant litter, but also from algae and aquatic biota as well. So the other component is that inorganic carbon component, and that's basically the CO2 and its derivatives, most of which comes from mineral weathering, from carbonates in particular, but also from the respiration, that is the breakdown of organic matter. When we respire, consume our lunch, we respire CO2, and as so goes in the environment. So we're basically looking at how, here I'll be focused on the organic matter component of the particulate. So POM refers to particulate organic matter, and DOM is dissolved organic matter. And that distinction is really just made based on what flows through a filter and what stays on top of it. So we use a 0.45 micron filter. If that organic particle is bigger than 0.45 and doesn't get through, it's particulate organic matter. If it's smaller than that, it becomes part of that dissolved component that we look at. All right. So nitrogen. Similarly, nitrogen has an organic side of the cycle. It also has an inorganic side. So again, the organic nitrogen, we're talking about that nitrogen that's built into cellular material from plants and biota. So proteins, amino acids, all of these organic molecules contain nitrogen. And then you have the inorganic component of the nitrogen cycle, which largely is derived from the breakdown or the mineralization of organic nitrogen into ammonia, and then the other biological processes which transform ammonia into things like nitrite and nitrate, so nitrification. The other process that brings inorganic nitrogen into a watershed or a soil system is nitrogen fixation, and that involves taking nitrogen out of the air as N2 and fixing it, converting it to ammonia. So when we refer to dissolved inorganic nitrogen, it's the sum of all of these blue species, and dissolved organic nitrogen refers to all of those other components of nitrogen that flow through that 0.45 filter, organic component. All right, so when we knew that these disturbances would have some impact on carbon and minerals are disturbed when active layer detachments happen. So this is a typical profile of what we expect to see in most permafrost zones. The active layer up here is pretty much been leached and stripped of a lot of the dissolved or easily soluble ions. So you have low concentrations of dissolved ions. Also, the plants and organic and the biota, microbes in the soil, take up all of that nitrogen, those inorganic components that the plants and the biota need to survive. So up here we have pretty low amounts of nitrogen, organic, with the exception of the organic matter. Organic matter, pretty high in the surface where the plant material is, in the organic soils, and then it decreases down. And for the most part, we're not really sure what happens beyond that active layer. We expect that the amount of carbon decreases, but until you actually do some analysis of what's below that frozen layer, you really don't know. So we know that we expect the inorganic components to increase when you get down below that sort of maximum, the usual depth of thaw. And this is a typical profile that you see pretty much anywhere where you have fine grain superficial sediments. So what we went about trying to figure out, well, if the disturbances remove this component and expose this now as your new active layer, what impact is that going to have on the downstream chemistry? So now all of a sudden, this layer of soil, which used to be frozen, is now exposed at the surface, susceptible to erosion, leaching, mineral weathering, and biogeochemical cycling. So we went on to look at various aspects of this to see how these disturbances influence that. So we started by looking at a number of different subcatchments, and this is all in the West River catchment. We picked some subcatchments where we saw there were different degrees of disturbance, so larger and smaller and more extensive disturbances. And you see, we looked at 5 different subcatchments with varying sort of percent areas that were disturbed. And luckily for us, 2 of these sites here, Ptarmigan, this watershed here, and Goose, this one here, we had actually been studying prior to the disturbance. So we have kind of a pre-disturbance baseline for those 2 watersheds. And after that 2007 disturbance, we started to monitor these other sites. Big Slide, ALD, and Caribou, which had sort of low to high degree of disturbance. So here's some images of what those disturbances look like. So Ptarmigan, about 12% of the catchment area was disturbed, but what was really remarkable about this is it happened right where the drainage, right along the sort of main drainage of that watershed. So water ran through most of the extent of that disturbance in that watershed. Goose, this catchment here, was not disturbed, remains undisturbed, and the water in this watershed sort of flows through this well-vegetated, mostly as water tracks and not very well channelized flow. And then some of the other disturbances look more like this. Again, highly disturbed with a lot of water running through them. Caribou here, although it had the same extent of disturbance as Ptarmigan, the flow pattern largely skirted around the disturbances. So although there were a lot of disturbances in this watershed, only a small area was actually hydrologically connected to disturbances. So keep that in mind as we go along. All right, so one of the first things we looked at when we started to study these impacts was how the particulate fluxes changed. And this included suspended sediment as well as the particulate organic carbon. So in this study, which was done in the 2008 melt season, we looked at the concentrations of suspended sediment and particulate organic carbon, as well as the age of that particulate organic carbon. So in this upper panel here, what you see in red is the suspended sediment concentration. The black dots here are the particulate organic carbon concentrations, and the two follow each other nicely. We actually have a beautiful relationship between suspended sediment and particulate organic carbon. And up here we have the radiocarbon dates of the particulate material that was in the stream at that time. And what we found from this study was that the age of the organic matter in the West River, which was more disturbed, more hydrologically connected to disturbances than the East River, we found that that particulate organic matter was about 15,000 to 3,000 years older than the organic matter that was dated in the equivalent times in the East River. I haven't shown that here, but what I wanted to show was that we determined that this was likely because of these disturbances, because we went in and sampled the particulate matter from the disturbed catchment, Ptarmigan, as well as the material from the Goose, the undisturbed catchment, and we found that this disturbed material had the oldest carbon dates that we found in all the particulate matter, and upwards of 6,000 years radiocarbon years, while the undisturbed Goose catchment had modern carbon values. So we know from this study that those disturbances are exporting older particulate organic carbon. So the other thing we said about doing this, well, okay, that's great, we know the age of it, but what does that carbon look like in terms of its biodegradability relative to the younger carbon from other regions? So in this study, we surveyed the suspended sediment material that was deposited along the West River from the headwaters up here down to the mouth of the river where it empties into the lake. And we looked at the molecular biomarkers and the molecular structures of the carbon in that particulate matter. And what we found from this study was that the fluvial sediments deposited along the West River reflected that downstream of these disturbed sites and in these disturbed tributaries, we found elevated amounts of the labile, or the highly biodegradable component of carbon relative to the upstream sites and the other undisturbed sites in the catchment. So higher amounts of the labile fraction and lower proportions of the aromatic components, which are not as easily biodegraded. So that's what's shown in, these are the disturbed subcatchments, and we found much greater peaks of those aromatics and, lower proportions of the aromatics and much higher peaks when it came to the more labile structures. And along with that, we also looked at some particular biomarkers in the soil organic matter taken from disturbed sites. And so here we have the concentrations of what are called PLFAs, and these are polyolipid fatty acids. And these are the molecules that make up the cell wall, the membranes of cell walls in microbial cells. And so we only find these when there's active microbial, there's a lot of microbial activity in the soil. So live active microbes. Because once the cells die, these compounds break down very quickly. So you don't see them after the microbes are dead and gone, because they break down. So what we found here is we looked at a number of sites. We looked at undisturbed sites, so we took soils from that Goose catchment where there's no disturbance. We took soils from the very recently disturbed sites. So this was done in 2008, so this was the season right immediately following those disturbances. And then we took samples from some areas where we know from air photos that there was and from looking at the land, there was a disturbance there and that it occurred somewhere on the order of 50, 60 years ago. So what we found was that in those areas where the soil was recently disturbed, that there was a high concentration of these polynucleate fatty acids, both the bacterial and the fungal fatty acids in these disturbed soils, relative to the undisturbed and the old disturbances as well. And so what this indicated to us is that, again, it's in part with what we just found with the NMR and biomarker results, is that the fact that the microbes were really active in these soils suggests that the disturbances release this very labile carbon that is easily accessible and that promotes this sort of microbial activity and carbon cycling in the soils. So that's kind of the particulate story. Then we set about looking at characterizing that dissolved component. Because the dissolved component, as far as the fluvial system, that's the carbon that's readily available to aquatic organisms and the aquatic food chain. So we started to look at how these disturbances affected the dissolved organic matter. And one of the studies we did, we characterized the age of the dissolved organic matter as collected from different areas where there was subsurface water, what we deemed to be subsurface water, in disturbed areas and undisturbed areas of the catchment. So we deemed this to be subsurface water because these waters were coming up either at breaks and slopes or in depressions where there was no surface water input, and this was collected late in the season when there was very deep thaw, and the only source of water at this point could really be subsurface flow. So some of the disturbed areas we sampled looked like this. There were these small ponds right within the active layer detachments. And what we found is that the areas where we sampled the DOM in these, where there was deep thaw or where there were disturbed sites, we had very old organic carbon. So what's being used, what this indicates is that dissolved organic carbon fraction within these disturbed areas or from waters deep within the active layer is delivering old organic matter. So this is not algae that's grown in these ponds. It's organic matter that's come from those older soils and sediments that were previously buried. The other thing we did that I haven't shown here, it's kind of still hot off the press type work, is that we also did the molecular characterization of this DOM and also found, similar to the particulate organic matter, we find higher proportions of that labile component, that easily degraded carbon, in the disturbed sites relative to the undisturbed surface water sites as well. Okay, so now I'm going to talk about some other ways in which we characterize the composition of the dissolved organic matter. One of the ways that it's frequently done, because it's simple and low-cost analysis that gives you a lot of information about the composition, that molecular composition of the carbon, is spectral tests, and in this case both fluorescence and absorbance. So I just wanted to explain what that technique involves and how it works. So optical characterization of the dissolved organic matter involves basically taking a light source, lighting up your sample, and the organic compounds in that sample, depending on their structures, whether they're aromatic or whether they have cyclic structures or linear chain structures, they have specific absorbance and fluorescence characteristics. So in this type of work, what we do is we shine a light source at a specific wavelength, and then we measure, for absorbance, we're measuring what is the intensity of light that shines through, and we take the difference as being the absorbance. And with fluorescence, what happens is you shine a specific wavelength on the sample, certain molecules get excited, and they, through the vibrational energies, they so by taking every sample and applying different excitation wavelengths, so exciting with different wavelengths of light, and measuring the absorbance and fluorescence of these samples, we can characterize the structures, at least those optical structures within the dissolved organic matter. So what we end up with are what we call emission excitation matrices. And so we excite our sample along different excitation wavelengths, and then we monitor the wavelength of light that's emitted at each of those across another extent of wavelengths here. And that produces this kind of map, if you will, of the topography of the dissolved organic matter. And depending on where these peaks occur, it tells us that there is very high amounts of proteins or humic-like fulvic acids, which are relatively low molecular weight. So again, these stuff in these zones we know is that easily biodegradable component. Whereas signatures up in this range tend to be higher molecular weight, more aromatic, harder to decompose organic matter. So this is indicative of material that's actually already been biodegraded over a long period of time, and this is easily available for biodegradation. So, so what we did in this study is we went around and we collected surface water runoff from the different subcatchments. So here we have ALD, the caribou goose, so the blue here, that's that undisturbed catchment. Ptarmigan is that most disturbed catchment. And caribou is relatively disturbed, but not really well connected to the disturbance, whereas ALD has a very small disturbance within it, but the river runs right through it. So what we found is that there's an increase in the freshness, a decrease in the molecular weight, so lower molecular weight, and a decrease in the degradation of the organic matter with disturbance. And also we found with rainfall runoff. So what we have here is the dissolved organic carbon concentration up in this slide here. And what we found, we plotted here, is what we call the freshness index. And so this is a fluorescence measurement. And so this is during the runoff season from early June to the end of July in these catchments. So this is right at the onset of snowmelt, early June. We see that the concentrations in all of these streams are pretty close, pretty similar. The highest concentrations are in the undisturbed site. Obviously, where you remove the surface soils, you're removing that source of organic matter, and so the more disturbed sites have lower concentrations of organic matter. In terms of the composition, we see increasing freshness and decreasing molecular weight as we go to the more disturbed sites relative to the undisturbed sites, which have higher molecular weight and lower freshness. So what we have here is one of the fluorescence components that was derived from our analyses of the emissions, the excitation emissions. And so this component 4 is basically highlighting this higher molecular weight organic carbon, and component 2 is slightly lower molecular weight humic acids. So what we find is that in these disturbed sites, ptarmigan, we have lower amounts of the high molecular weight humic acid components, and especially we also see that following the late summer rainfall, we see lower amounts of that humic acid component as well. So we've seen fresher, lower molecular weight material with disturbance and with rainfall. And again, this is looking at some of the other components, the low molecular weight and the proteinaceous components. So again, lower molecular weight components, higher amounts of proteins in the disturbed sites, And and especially here, we see it right there at the end of snowmelt. There's a big switch between the undisturbed and the disturbed materials here in terms of that proteinaceous component. All right, so as far as the organic matter goes, the dissolved story, the particulate story, they're all telling us the same thing. The material that's coming from these disturbed areas is older, no surprise. But what is surprising is that it was always thought that the older the carbon, well, outside of permafrost areas, it makes sense that the older the carbon, the more degraded it's going to be, the less fresh it's going to be. Well, in permafrost environments, that organic matter that's deeper in the soils may have been there a long time, but has been frozen a long time. And so there hasn't been opportunity for microbial biodegradation of that material. So it's still old, but it's relatively fresh and labile. So that's what we determined from that. And another study, we were looking at the nitrogen. So nitrogen is a really important nutrient that all plants and aquatic organisms need. And so we knew that changes in the amount of soil covering an area and the changes in the organic matter would alter the nitrogen story somehow. So what we have here are results from goose and ptarmigan. So those two streams that we started studying in 2007. So here's our pre-disturbance goose and ptarmigan results. So this is 2007. Up here we have the discharge. Here we have ammonia concentrations in the water, and down in this lower panel are nitrate concentrations. 2012, 5 years after disturbance, we found that we had, well, higher discharge in this year. 2012 was also a relatively warm year, kind of similar to 2007, not quite as hot. So we saw that both catchments saw an increase in ammonia concentrations, but they both followed each other relatively closely when it came to ammonia. But we saw, however, a really big difference in terms of the amount of nitrate that came out of the ptarmigan catchment. So that disturbed catchment all of a sudden is delivering much higher concentrations of nitrate, not only during snowmelt, during base flow, but particularly following rainfall events in later in the summer. So one of the questions that remained after we saw that was, where on earth is this nitrate coming from? Because it could be coming from deep mineral soils, it could be coming from extra atmospheric deposition, because one of the things we know about disturbances is because now you have a depression on the landscape, these depressions tend to accumulate more snow. And so possibly that extra nitrogen, one of the sources of nitrate in the atmosphere is rainfall. So we thought, okay, maybe it's atmospheric. Maybe it's snow melt delivering more nitrate to these catchments. Well, so what we have here is a study where we looked at the stable isotopes of oxygen, so the oxygen molecule of nitrate, and the stable isotope of nitrogen on that same molecule of nitrate. And we know from previous studies, but also from our own work, that the atmospheric nitrate, the oxygen stable isotopes in the atmospherically sourced nitrate are very high stable isotope ratios. And that's simply because of the atmospheric processes that impart very high stable isotope ratios there. So when we looked at the nitrate in our waters, so again we have the goose during the snowmelt here in yellow, and the blue is ptarmigan. During that initial snowmelt period here, the runoff, the nitrate in the waters was very much the same as that atmospheric source. So that first pulse of nitrate through both those streams was definitely from snowmelt. But as soon as we move into this sort of lower base flow, the recession flow, the base flow period, all that in ptarmigan was found to be derived from microbial mineralization of the nitrate. So the nitrate's being produced either from mineralization of that organic nitrogen that's being converted to ammonia and then nitrified to nitrate, or it's ammonia that's just being nitrified. So when we look down here at this time of the year, but also during this rainfall event, all of that nitrogen is actually microbially produced in that ptarmigan catchment. So that elevated nitrate that we found following disturbance is also the result of microbial mineralization. So this story holds well with what we found with the PLFAs in the soils, that after disturbance, that disturbance event allows for this enhanced sort of microbial activity in these disturbed areas. And again, this all meshes well with what we found with the carbon story as well. So with all of this work points to, from all these different studies, point to the same sort of conclusions, that organic carbon, whether particulate or dissolved, when it's coming from the deep active layer or the active layer that was, or the sort of the permafrost table that was brought to the surface after disturbance, that carbon is substantially older than we find in the upper soils or from undisturbed sites. And furthermore, the composition, that is the nature of that carbon, is less degraded, so it's more labile than that carbon from the surface soils or in undisturbed regions. And the PLFAs in the soils, that microbially derived nitrate, confirms that that carbon that's exposed is highly bioavailable, and it is promoting high amounts of microbial activity and carbon cycling within these systems. So these results also are in keeping with studies that have been done in other areas of the Arctic, in Alaska, and also in a couple of sites across in Russia, that indicate that our initial conceptual models that we thought, permafrost carbon was old, but it was going to be highly degraded and not very bioavailable. Well, now all of a sudden there's this new take on things, that just because it's old doesn't mean it's not fresh. And in permafrost environments, old is typically fresh, which goes against what we find in most other environments. So in the end, this whole study is about us thinking about, so how are these changes likely to sort of propagate into the future as climate warms, as potentially as rainfall increases. And so these studies have really pointed to the fact that thaw depth and rainfall are likely to be really important controls on both the magnitude and the temporal dynamics of carbon and nitrogen responses in these systems moving forward. So in other words, the deeper the thaw, the more likely you're going to tap into these ion-rich, potentially nutrient-rich, deeper layers of the soil. If you have rainfall events in late summer when the thaw has propagated to depth, even if you're not exposing that to the surface, if water is getting in and moving through that layer, we have the potential to export nutrients and highly bioavailable dissolved organic matter. And so that rainfall being the vector and the thaw being what releases and releases that carbon that's from below. So thaw and or disturbance, which will remove the surface material. And I think that's it.
Est-ce qu'on aurait des questions dans la salle? Oui?
Je peux poser la question en français?
Oui.
Parfait. présentement et dans le futur? À quoi est-ce qu'on peut s'attendre?
Ben, on s'attendait qu'il y aurait une augmentation, mais c'est encore, ce qu'on découvre, c'est que c'est encore très compliqué. Parce que ça dépend beaucoup de ce qui se passe dans les lacs eux-mêmes. I'm sorry, I'm going to flip to English again. So we have been looking at Westlake and Eastlake chemistry and dynamics. And what we find actually is through these very large lakes, the river inflows aren't really what are the drivers in terms of the chemistry in these lakes. And what's happened over this time period of the disturbance in the landscape, we've also found that there's actually subaqueous disturbances happening within Westlake that we haven't seen in Eastlake. So I don't know, Mother Nature's been really kind to us up there because she's sort of thrown us this experiment in situ of what happens when you disturb one aspect, one thing and not the other. And so what we're finding is that the disturbances are leading to all sorts of other types of impacts on the biota, the aqueous system. So one of the things is turbidity, when there's these subaqueous slumps or disturbances. So the turbidity in Westlake has gone up a lot, and that has had an observable impact on the fish health, their size, and mass, their weight is decreasing since this, because what happens is the fish, they feed by sight, and now they can't see their prey, because you have all this, and it's evident. I mean, we used to take samples from the lakes and we could filter them like no problem. Now you take a sample and it's like you can't see through it. It takes you forever to filter. So this is having an impact on the biota. And the other thing that we're seeing is it's contaminants coming from the sediments and things are changing as well. So what we're seeing on the aquatic ecosystem side, the impacts that we're seeing are not necessarily related to the nutrients, because there are these other bigger things that are having the more, the impacts. So we haven't really been able to link this nutrient story the way we thought we might, because of all the other things that are going on.
How do you see so there's basically the new active layer is full of labile carbon, both dissolved and not dissolved. How fast do you see the fraction of that changing to what could have been before? So what would be the rate of change, and how would you reach a new equilibrium? How fast would it be before a new equilibrium is changed?
That's probably, I could say that we still haven't really quite answered that. All that we can say is that these studies we've done 5 years after disturbance, we're still seeing an observable impact. So we know that they can last up to 5 years. I think we still have yet to see how much longer that might occur. I suspect it's not as long as, I think we're going to start to see it taper off. And it's just a function of the things are happening so quickly, and the carbon is there, it's very labile, but there's not that much of it. It's the other thing, when you compare the amount of carbon in the surface soils versus what we find deep down, there's a lot less of it.
Can I follow up?
Yeah, sure.
You said you were measuring fluxes, carbon fluxes
Yep.
as well in the watershed, or throughout the watersheds. I guess the footprint isn't very large for the flux tower.
Oh, the flux tower.
Yes.
It's, how large is the footprint? That's a good question. It's a few kilometers for sure.
Oh, okay.
Yeah,
so
a few square kilometers.
I mean, disturbances are relatively small. Has there been any observable change in the
No, because the flux tower is in an area that hasn't been disturbed.
Okay.
But there have been studies that have looked at the gas exchanges in the disturbed sites. And these were done not using the flux tower, but just with chamber measurements over the course of the season. And there was actually, I think, a decrease in the actual fluxes. And it's just, there's less carbon there. So I think that's been, I don't know that that study's been published yet, though. I think that work's been published.
How did you do that in Eureka?
Yeah, Ollie did it in Eureka. Allison Beamish did some at Cape Bounty. And I think maybe it was published, but I'm a bit confused over whether it was the, she also looked at the trace gas, like the nitrogen fluxes too, so I'm not sure if that publication dealt with all of the gas fluxes or just the nitrogen. But yeah, Beamish et al. It's not on there.
Est-ce que l'arrivée de nouvelles bactéries fixatrices d'azote peut favoriser l'activité d'une transition végétale?
Ça se peut. Puis, en fait, on a fait très peu d'études vis-à-vis des communautés, the microbial communities. But the little bit of work we did, we actually found there's a big change, at least in the fungal communities, between the disturbance and the undisturbed sites. And some of the changes are to do with these nitrogen bacteria, so we're aiming to do some follow-up work to look at that specifically. Because, I mean, this story that we saw is just kind of, well, suggests something pretty significant has changed.
Yeah.
So yeah, that the study that I'm referring to is still in press, but I'm hoping to get it out there soon. Yes.
How much do you think of the export is actually sedimented? Like if you go further down the stream, and is it sedimented in lakes, ocean?
Well, in this setting, all of the sediment export ends up in the lakes,
Okay.
and settles out in the lakes over time.
Is there any work on looking how the sediment export actually changes the lake downstream, the sediment?
Yes, so we have published study looking at the sediment loads and how they were affected by the disturbances. So that is, I think it's 2009. Yeah, and then there's also work continuing. So they're looking at sort of the longer term pictures since then. And there's also been work looking at the sediment accumulation in the lakes. That bit hasn't been published yet. But yeah, it's definitely something that we're looking at, but it hasn't been published yet.
Je vais prendre une dernière question. Adrien, je te
More about the active layer detection. What would be the optimal condition to observe those processes, and did you observe more and more active layer detachments since you work in Cape Bounty?
Yeah, well, we haven't seen any more active layer detachments since 2007. What we have seen in just outside of our catchment boundaries are retrogressive fossils, and those are actively slumping and retrogressing. The ptarmigan active layer detachment has been retrogressing over time as well, so that one's still actively slumping at the head start.
So
But everything else is pretty well stabilized, other than the sediments just being moved around. But
so you will relate that more to extreme, like warm summer?
yeah, so it would take another warm summer followed by, and I think the warming was pretty extreme, but the timing of the rainfall, because there was if I go back to that first slide, there was the warming, there was some minimal rainfall, and then there was more warmth, and then a really big rainfall. So there was this sort of complete saturation of that active layer, and that just sent it all sliding. So it would have to take something similar, at least in this area. But we know from the coring work that Michelle has done is that there's a lot of areas that have a lot of ground ice, so it's not inconceivable that there would be more